Right, in this video we're going to try to connect the calorimetry, so that's the heat transferred, to the enthalpy of a reaction or enthalpy of a change, and then can connect that to a chemical reaction's molar enthalpy and the number of mole. This covers most of the math in this unit of thermochemistry. The problem is that this looks like the dumbest thing you've probably ever seen. First of all, this drives me crazy. Because of the symbols, enthalpy is equal to the number of moles times the enthalpy, is the way it looks. But what you need to know is that we have the same symbol for molar enthalpy as reaction enthalpy. It's not well denoted by the symbols. But the number of moles times kilojoule per mole would give you kilojoules, right? Because the moles would cancel out. Well, kilojoules are going to be equal to kilojoules. The enthalpy change in the reaction is going to be equal to the calorimeter's heat exchange or heat transfer. And that kilojoule would be equal to mc delta T, because you'll remember that the mass, if it were in kilograms, times the joules per gram degrees Celsius times degrees Celsius will be kilojoules. So all of these values are related. The thing is that this is in our calorimeter. That's how we measure it. This is going to be the same value. This is going to be the same value. And if I know the number of moles that react, then the number of moles times the molar enthalpy will be the same value as this. So these two things end up being connected. This is all based on the concept of conservation of energy. So the energy of this reaction is going to be same as the energy that caused the change in the calorimeter, as long as we're not losing energy to the environment. And we've got a closed system that we try to make isolated by insulating the reaction vessel. So if we can capture all that heat, then it'll be the same value as the number of moles times the molar enthalpy, which will be the same as the enthalpy, which is the same as the heat transfer, which we measured in the calorimeter. So if the number of moles times the molar enthalpy equals mc delta T, then it gives us a lot of power. As long as I can calculate the mc delta T, if I want to find the molar enthalpy, it'll be mc delta T divided by N. Again, this is fine. It's not bad for math, but if you just understand the units, again, if we have kilojoules, or kilograms, sorry, times joules per gram degrees Celsius, times the degrees Celsius, that gives us our kilojoules, and divided by mole, that'll give us kilojoule per mole, which is the units of molar enthalpy. So while this seems like it's quite confusing, once we get into questions, it's going to start to make sense. Because the other thing that we can do is if N is delta H equals, I'm starting to run off the page here. If N equals N times delta H equals mc delta T, if I want to know how much temperature change there is, but I know this and this and this and this, I can calculate delta T. It's going to be equal to N delta H divided by mc. Right, so I just take these values and put them down here. Since it's all multiplication, it's pretty straightforward. And that's going to be at the heart of most of the questions that we end up having related to calorimeters, enthalpy, and molar enthalpy. So if I wanted to calculate just the enthalpy of an enthalpy change, it'll be equal to mc delta T, or the enthalpy change would be equal to N delta H if this is molar enthalpy. And if I want to calculate the amount of change, then I need to know the number of moles and the molar enthalpy and mc delta T. And now if I know this, I can calculate one of these if I have the other values.